Hello, everyone. Welcome to this talk. I'm Zixuan Wang, a PhD student from UC San Diego, working with Professor Jishen Zhao. Today, I'm going to present our paper on NVLeak off-chip side-channel attacks on non-volatile memory systems. In this project, we reverse engineered the hardware design of a non-volatile memory product, and then developed a set of side-channel and covert channel attacks to leak information through this hardware. I will first introduce the background and motivation, and then discuss our reverse engineering results and corresponding attacks. So the non-volatile memory is a new type of memory that works like a traditional DRAM. It is byte addressable and sits on the memory bus. But its data is also persistent, so a system reboot will not cause data loss in the non-volatile memory. So since it looks like a DRAM, we would expect its hardware design to be similar to DRAM. But in fact, it's more complicated. Our prior research paper published on Micro 2020 shows that non-volatile memory has a very complex architecture design. We find the right pending queue in the CPU memory controller that handles the write request to the non-volatile memories. Inside the non-volatile memory module, we find a load store queue together with two levels of data buffers, each with a different block size. We also discovered a data migration mechanism for very leveling purpose, just like how SSD works. But we still have several questions not answered by our prior work. For example, are these buffers just naive buffers, or are they caches? And if they are caches, what's the set associativity and replacement policy? And regarding the data migration, we want to know if it is timing sensitive. All these questions are critical to the non-volatile memory security, and if we can find the answers, we can develop architecture-level side and covert channel attacks, and then we can investigate how to design future non-volatile memory that makes it safer. As an overview, in this project, we reverse engineered more architecture-level designs of the non-volatile memory and found some designs enabling architecture-level attacks. We then demonstrated corresponding attacks and mitigations. So based on our prior research, we know there are multiple buffers in the non-volatile memory DIMM, organized as a hierarchy. But we really want to know if they are buffers or caches, because caches are more vulnerable to the side-channel attacks. To solve this problem, we conduct a software-based reverse engineering to find out the non-volatile memory cache designs. We use a strategic memory access to reverse engineer the caches. By changing the stride size and monitoring the memory access latency changes, we can detect the cache set size. Here, I will first use a set of examples to explain how it works, and then go to the results on the real hardware. Here's an example of using strategic memory access to detect the cache set size. Assuming we have a non-volatile memory cache with 4 sets, 2 cache blocks per set. We first use a stride size equal to the cache block size, which is effectively a sequential access. And we measure the latency per cache block access. And we access the first block, get a low access latency. And then the second access is still a low latency. So on and so forth. Until we access the nice block, it triggers a cache conflict and we see a higher latency. And next step, we double the stride size to be 2 times the block size. We access the first few blocks, they are all low latency. And starting from the 5th block, we get a higher latency. And after that, we get even higher latencies. And similarly, we double the stride size again, we get first 2 blocks of the low latency, and starting from the 3rd, we get higher latencies. And after this point, if we double the stride size again, we still get first 2 cache sets as low latency, but after the 3rd one, we get higher latency. So looking at all these latencies, the overflow point starts from 8, then goes to 2, and it stays at 2. This means when all access go to the same cache set, in this case, 2 cache blocks is enough to overflow 1 cache set, which further means we detect a cache set size as 2 blocks, or in other words, it's a 2-way set associative cache. So now let's look at the results on the real hardware. Here we analyze the L2 NVCache as an example. So in this result plot, the x-axis is the memory access size in number of blocks, and y-axis shows the memory access latency per block. These 2 lines show the read and write latency separately. We start with the stride size equal to the L2 cache block size, and observe that overflow point is 4 kilo blocks. When we set the stride size to be 2 times the cache block size, the overflow happens at 2K blocks. And after that, 1K, 512, so on and so forth. Until we come to the stride size equal to 256 cache block size, we see the overflow point is at 16 blocks. And after that, if we still double the stride size, the overflow point stays at 16 blocks, which, based on our prior example, this means that the L2 cache is a 16-way set-associative cache. So similarly, we reverse engineer other levels of caches in this way. But due to the time limit, we cannot present all the reverse engineering details. In summary, we find that non-volatile memory DIMM has two levels of cache built in. The L1 NVCache is 16 kilobyte size with 256 byte blocks, and it is fully associated. And the L2 NVCache is 16 megabyte size with 4 kilobyte blocks, and is 16-way set associated. We also find that where leveling data migration happens once per 16K writes, and each time it migrates a 4 kilobyte block. Based on these reverse engineering results, we can develop the side channel attacks. Here we first demonstrate an example side channel attack that leverages the NVCache to leak the database operations. We assume that the victim is a database application that executes normal SQL queries and data stored in a DEX file system on non-volatile memory. An attacker is just another process that shares the non-volatile memory DIMM with the database, but there's no overlapped shared memory. Or in other words, the attacker and victim shares the non-volatile memory hardware, but they are using different memory regions. In this threat model, the attacker can monitor the access latency of the NVCache blocks and further detect the victim SQL operations. So here's a more detailed illustration of this attack, and it involves 3 steps. In step 1, the attacker prepares the NVCache, it reads memory from the non-volatile memory, and the NVCache is filled with the attacker data. And the next step, the attacker waits for the victim activity, and victim executes the SQL code, which accesses the part of the non-volatile memory and fills corresponding NVCache sets. Then attacker comes back and reads memory set by set. It detects a few sets that has conflicts. So attacker performs these steps repeatedly to trace the victim memory access and use this trace to categorize different SQL code from the victim side. So here's part of the SQL code we studied in this project, which include updates, counts, queries, and insertions. More SQL code is shown in our paper. We set up the SQLite database by using NPPES dataset and execute this SQL code in the victim database. So when executing the victim SQL code, the attacker performs the side channel attack and gets the victim memory access trace. Here, each plot shows the access trace of a single SQL execution. Each bottom plot, x-axis is the side channel iteration, and y-axis is the L2 NVCache set number. Each point indicates the corresponding cache set is accessed by the victim in that iteration. And each top plot shows the access latency distribution. We notice that different SQL code generates different access patterns, which can be categorized by the attacker to learn which type of SQL code is being executed by the victim. So we then present a side channel attack to the Wolf SSL library that can leak the private keys. In this attack, we assume the non-volatile memory is used in memory mode, where it works like a traditional DRAM memory and it holds the code pages from programs. We assume the victim is a process using Wolf SSL to encrypt data. The attacker actively flushes the code cache lines from L1 NVCache and types the access to the shared Wolf SSL code. Whenever the attacker observes a low latency access to the cache line holding the function, it means the corresponding L1 NVCache line is loaded by the victim, and in this case, the attacker detects one victim call. By repeatedly timing the selected function, we demonstrated that attacker can recover more than 28% bits of the private key, which has a very high probability to recover the full key. So in conclusion, in this project, we demonstrated a detailed microarchitecture reverse engineering of commercial non-volatile memory products and discovered on-DIMM microarchitecture, including NVCache and data migration mechanisms. Based on these architectural components, we performed a few attacks, including cross-virtual machine covert channel, database side channel that leaks type of SQL code being executed, and also the conditions on the range query, which can lead to full database leakage. And we also demonstrated a Wolf SSL side channel, which leaks the private key. We also demonstrated a cross-file system covert channel using a data migration mechanism. Finally, we described the mitigations, implemented a software-based mitigation in TMDK, and evaluated its performance overhead, which turned out to be marginal. We open sourced our code on GitHub, and here's a link. So this is our project, NVLeak, off-chip side-channel attacks via non-time memory systems. This concludes my talk today, and I can take some questions. Thank you.